All right, guys. So I'm recording from home and I'm using new software, so hopefully all this works. I'm also using an actual mic, so hopefully you'll be able to hear me better. Hopefully you will not have to listen to me breathe or anything. Let's go ahead and get started. I'm working the waves and light calculations 2 that you got today. It's a half page. The equations that we're going to be using to work this are pretty simple. We have the equation for the velocity of a wave. If you hear noises in the background, it is my dogs, and I'm sorry. So the equation for the velocity of a wave is that the velocity is equal to the wavelength times the frequency. We also know that the energy of a wave is equal to Planck's constant times the frequency. Planck's constant is 6.63 times 10 to the negative 34th joule seconds. And then the last equation we may need is the first equation you learned in our whole class, V equals D over T. All right, let me get the calculator app running on my phone. All right, we should be good to go. The first problem, heat lamps produce a frequency of 1.09 times 10 to the 9th hertz. What is the wavelength? Oh, there's actually an important piece of information up here that we didn't add. I'll add it in just a second. So what they've given us, F equals 1.09 times 10 to the 9th hertz. They're asking us for wavelength. And you may be thinking, Ms. Schneider, that's not enough information to work this problem. And you would be right. But see, there's something we know that I didn't write up here. We know that the speed of light is always 3 times 10 to the 8th meters per second. Doesn't matter what kind of light. And when I say light here, I mean electromagnetic wave. So any kind of electromagnetic wave moves at 3 times 10 to the 8th meters per second. So here, our velocity is equal to 3 times 10 to the 8th meters per second. So then we just have to use our first formula, and it's basic plug and chug. V equals lambda F. So 3 times 10 to the 8th equals lambda times 1.09 times 10 to the 9th. So we're going to divide both sides by 1.09 times 10 to the 9th. Remember that I said in this unit it is super important that you make sure you know how to plug exponents into your calculator correctly, because when you are dividing by exponents, things can get real squirrely real fast. So plugging this in correctly, I am getting that lambda equals 0.275. You could put 0.28. That would be fine. I don't care. And that is in meters. And that should make pretty good sense to you because that's a pretty high frequency, 10 to the 9th. High frequency is going to mean small wavelength because they are inversely related by this equation. All right, let's look at the next one. Grandpa Jim calls James on the shortwave radio from his home in Toccoa, which is 157 kilometers from Snellville. How much time will it take James to hear the CQ call from Grandpa? So here's what we've been told. We know that our distance away, Gumshoe, you're the worst, shut up, is 157 kilometers. We don't care about that, though. We don't care about kilometers. We care about meters. So that's times 1,000. So we're going to add 3 zeros. Meters. And then we're going to remember that a radio wave It's just a light wave. So we know the velocity again. V equals C equals 3 times 10 to the 8th meters per second. So we are looking for time. We are going to use our intro baby equation. V equals d over t. We have 3 times 10 to the 8th equals 157,000 over t. So we're actually going to cross multiply to get t by itself. So to get t by itself, we do 157,000 divided by 3 times 10 to the 8th. Make sure that you are doing your exponents correctly. I'm going to actually plug this into my calculator to make sure I'm doing everything correctly. Even I make mistakes. And I plugged that in totally wrong. So yeah, let me try that again. All right, 157,000 divided by 3 times 10 to the 8th. There we go. I am getting 0.123 52 seconds. You could also write that as 1, 2, 3, 4, 5.2 times 10 to the negative to the negative 4th seconds. This is why if you're talking to someone on the radio, it seems basically instantaneous. It's not actually instantaneous. It is taking time. It's just taking a really small amount of time because light waves travel really fast. All right, number 3, the official school's closed message comes from AM 750 WSB, that is 750 kilohertz. What is the wavelength for WSB? What is the energy for WSB? All right, so they've given us frequency, and they've given us 750 kilohertz, which is times 10 to the 6th. And then the first thing we're being asked for is wavelength. Then we are being asked for energy. And the other thing we know, as in every problem, is that the velocity is 3 times 10 to the 8th meters per second. So to do the first part, it's very similar to number 1. We're just going to use V equals lambda F. 3 times 10 to the 8th equals lambda times 750 times 10 to the 6th. This should have a longer wavelength than number 1 did because it has a smaller frequency than number 1 did. That makes sense because this is a radio wave and that was an IR wave. So divide both sides by 750 times 10 to the 6th. Sorry, my husband came home and I completely lost my train of thought. I believe that we were dividing by 750 times 10 to the 6th. And if we plug that into our handy dandy calculator, we get that the wavelength is 400. Is 400 meters. I haven't left myself a whole lot of room here. I'm going to fix that. I hate mechanical pencils. You'll notice I never use them in class, but it's what I have home with me. All right, so we officially are having technical difficulties with the new software. because I am having to redo these next few problems. So if it seems like I'm kind of rushing through them, I am. All right, so the second part of this problem asks what the energy of the radio wave is. So we're going to use this equation that we haven't used yet. E equals hf, where f is the frequency, which is 750 times 10 to the 6th hertz. Pencil. And h is Planck's constant, so it's 6.63 times 10 to the negative 34th. This is just simple multiplication. As long as you can plug the nasty-looking Planck's constant into your calculator, you should be fine. Hopefully, just by looking at this, you can tell it's going to be a really tiny number because you're multiplying negative 34 times positive 6. And you do, in fact, get an answer of 4.97 times 10 to the negative 28th joules. This is why a radio wave can pass through your body and it not be a big deal at all. Or actually, it wouldn't pass through your body. It would hit your body and it would not be a big deal because it has so little energy. All right, moving right along. Number 4. Light from the sun has about a 7-minute delay from its production to the time it reaches Earth. How far away is the sun from the Earth using this average time? Oh, before I get started working on this, if you are in my first period class, the answer that is written down is incorrect. If you're in my fourth period class, hooray! I corrected this before I printed the sheet out for you. It treated it like it was an echo problem. It's not an echo problem. The light is not having to make a round trip anywhere. It's coming straight from the Earth to the sun. So anyway, my husband pointed out, yes, he is creepily listening to me record this, that I'd said it backwards. Light does in fact go from the sun to the Earth, not the other way around. Anyway, so here's what they give us in the problem. They tell us their time is 7 minutes. And that's actually all they tell us. The other piece of information we have is the fact that the velocity is equal to c, which is 3 times 10 to the 8th, because it's light. Always moves at the speed of light. And we're looking for distance. So this is going to be a relatively simple problem. V equals d over t. However, before we can start plugging anything in, we have to take care of this. They gave us the time in minutes. We never work in minutes, never ever. We always convert to seconds. So 7 minutes times 60 gives us 420 seconds. Once you do that, then it's just plug and chug. 3 times 10 to the 8th equals d over 420. Cross multiply, 3 times 10 to the 8th times 420 gives us a distance of 1.26 times 10 to the positive 11th meters. I think that the time it takes for light to reach us from the sun is closer to 8 minutes, so this is probably a little shorter, but this is relatively close to being accurate numbers for the Earth-Sun distance. Number 5 is very similar. It has a similar setup and everything. Number 5 says the planet Saturn is 1.27 times 10 to the 12th meters away from Earth. How much time did it take for Cassini's pictures of Saturn's rings to transmit back to scientists on Earth? Cassini was a, I forgot how to words, probe. I officially hate teaching with my husband in the room. Cassini was a probe that we sent to take pictures of the outer planets. So here they've given us the distance, which is 1.27 times 10 to the 12th meters. V equals C equals 3 times 10 to the 8th meters per second. And we are looking for time. Now, So the setup of this problem is very similar to the problem number 4. The execution of the problem is actually similar to number 2 because it's time that we're looking for. So V equals D over T, 3 times 10 to the 8th equals 1.27 times 10 to the 12th over T. So we're going to cross multiply and then cross divide, which I do in kind of one step. So I end up with 1.27 times 10 to the 12th divided by 3 times 10 to the 8th. And we end up with an answer that can be written two ways. It can be written as 4,240 seconds or 4.2 times 10 to the 3rd seconds. So it actually takes light longer to get from Saturn to us than it does from the sun to us because we are closer to the sun than we are to Saturn. Today you learned. All right, number 6. It takes light from Alpha Centauri 1.38 times 10 to the 8th seconds to reach the Earth. How far away is the star? Alpha Centauri is the closest star to us, and it still takes 10 to the 8th seconds for light to reach us. So, T equals 1.38 times 10 to the 8th. V equals C equals 3 times 10 to the 8th. And we are looking for D. V equals D over T. 3 times 10 to the 8th equals D over 1.38 times 10 to the 8th. You cross multiply, so you're just multiplying these two numbers together. Again, make sure you're watching your exponents, and we get 4.13 times 10 to the 16th meters. Quite a ways. I'm not 100% sure how accurate these numbers are. Mr. Bell, I think, wrote these problems, and he said that particularly for my benefit, he tried to make them pretty accurate. Joke's on him because I don't happen to know off the top of my head how far away Saturn is or Alpha Centauri, so I'm just going to assume that these numbers are right, or at least close to right. When you're dealing with things this big, close to right is good enough. All right, last but not least, number 7. What is the wavelength range of AM radio waves? The low side has a frequency of 580 kilohertz, and the high side has a frequency of 1,710 kilohertz. This is actually two problems masquerading as one problem, but it's two easy problems. Basically, it's giving us two different frequencies, 580 times 10 to the 6th, and 1,710 times 10 to the 6th, and it wants us to find the wavelength for both of those. So V equals C equals 3 times 10 to the 8th. We are looking for lambda. We are going to use velocity equals wavelength times frequency. 3 times 10 to the 8th equals wavelength times 580 times 10 to the 6th. I hate lead pencils. Sorry, I am on the struggle bus.